Hey guys, now in this video we shall see the concepts in torsion. Actually, what is torsion? Torsion is the rotation about longitudinal axis. Let's start with the first question. The theory of pure torsion is based on the following assumptions. So this question is purely based on the assumptions we are following in pure torsion theory. Option A, material of the shaft is uniform. Option B, torque along the shaft may not be uniform. And option C, all radii which are straight before twist remain straight after twist. And last option is cross section of the shaft remains plane even after twisting. So among these four options, what are the correct assumptions? Now let's see those things. So option A, C and D, that is material of the shaft is uniform throughout, is one of the assumptions we are following in theory of pure torsion. And the torque along the shaft may not be uniform. It is wrong. Like torque along the shaft should be uniform. This is the assumption. That's why this option is not correct. And option C is all radii which are straight before twist remain straight even after the twist. This is also a correct assumption. Cross section of the shaft remains plane even after twisting. Now let's see more assumptions about theory of pure torsion. Basically, material is to be isotropic, homogeneous, and linear elastic. So here, linear elastic refers to the Hooke's law. Hooke's law means there is a proportionality between stress and strain. So that therefore, here Hooke's law is valid. That means the material is linearly elastic. The torque is applied about the axis of the shaft. So we have just now seen like a torsion. What is torsion? This is the rotation about the longitudinal axis. This is the rotation about the longitudinal axis, unlike bending moment. Bending moment is that is a rotation about transverse axis. Here torsion means rotation about longitudinal axis, so that's why torque is applied about the axis of the shaft. It's one of the major assumptions. For non-circular sections, the shear stress distribution is non-uniform. So that is why we are using only the circular shafts, not some other shaft like rectangular or triangular or square. Circular shafts are used because of the uniform shear stress distribution. And in case of non-circular sections, warping may occur. Warping means a type of bending. Bending may occur in case of non-circular sections. So that is why non-circular sections are torsionally weak. This is one of the major point to be noted. And next point, shear stresses are developed in two mutually perpendicular planes. And last one is no shear stress in radial direction. In the radial direction, like r direction, there will be no shear stress. Now let's move on to next question. Before moving to next question, we shall just see the shear stress distribution in case of torsion applied. In case of the torque applied and torsion is generated as a reaction. So here you can see this is a circular shaft. Here we are applying a couple. So that is why twisting happens. And this is the angle of twist. This theta or phi is the angle of twist. And shear stress distribution is as follows. This is the shear stress distribution. You can see here. First here 0, and at the radius of the shaft, it is at about capital R, the shear stress is maximum. And this equation is the basic equation for pure torsion. T by J equal to tau by R equal to G theta by L. What is T? The torque applied. What is J? J is the polar moment of inertia, that is nothing but twice the moment of inertia. For example, J is equal to 2 times Ix. For example, if you are considering circular section, what is the moment of inertia? That we know b d cube by 64. So 2 into b cube by 64, pi d cube by 64 gives uh, pi d cube by 32. So that is the polar moment of inertia of circular section. And tau is shear stress, r is the radius at that section. For example, if you are considering this section, then what is the radius? And g is the shear modulus, theta is the angle of twist, and L is the length of the shaft. So torque, polar moment of inertia, shear stress, radius at that section, shear modulus, angle of twist, and length of the shaft. Now let's move on to second question. This question is a simple problematic numerical type question. When subjected to torque, a circular shaft undergoes a twist of 1 degree. So they have given angle of twist, and the length of the shaft is 1200 mm. The maximum shear stress induced is 80 megapascal. The modulus of rigidity of the material given us 80 gigapascal, and we have to find what is the radius of the shaft. Here we have to use that pure torsion formula, T by J equal to tau by R equal to G theta by L, and just substitute all the given data over here, so that we can get the answer for radius of this shaft. Here the answer is option D, 216 by pi. Now let's see the substitution, how we are getting it. So here we have to find this small r value, right? This small r value has to be found. They have given theta, and shear modulus, that is modulus of rigidity, is also given as, that is nothing but G is equal to 80 GPa. We have to convert into Newton per mm square, so that is nothing but 8 into 10 power 4, and theta in radians divided by L. L, what is the length of the shaft? 1200 mm, and theta should be in radian. So here they have given 1 degree, so 1 degree is equal to 1 into 180 by 5 radians, and maximum shear stress induced is 80 MPa, that also given. So use this relation alone to get the answer for the radius of shaft. To get the answer for radius of shaft, we have to use only the maximum shear stress. So maximum shear stress occurs at the outermost edge of this shaft, that is the radius of the shaft, as we have seen in the previous diagram. So this is how we have to calculate and substitute all the data, so that we can calculate the radius of the shaft. Now we shall see more points regarding torsional rigidity, stiffness and flexibility. So Gj is nothing but torsional rigidity. So here you can see this is G and J. What is J? Polar moment of inertia. So G into J is equal to torsional rigidity, and Gj by L is stiffness. This is analogous to axial rigidity and axial stiffness, right? Similarly, we have to follow, right? For example, axial rigidity is given by E into I. Flexural rigidity, we can say flexural rigidity is E into I. So similarly, torsional rigidity is G into J. These are some analogous, and stiffness is Gj by L, and in case of axial, Ei by L. In case of torsional stiffness, Gj by L, and flexibility is the inverse of stiffness. So simply we have to follow the things. If they ask what is torsional rigidity, then Gj is the answer. G into J, that is the unit is in Newton meter square, and for stiffness, Newton meter per radian, and for flexibility, radian per Newton meter. So these are some important extra things to be aware of. Now let's move on to third question. This question deals with the power transmitted by the shafts. So here they have given two steel shafts A and B are used for transmitting power. The ratio of revolutions of shafts is 2. So that is revolutions RPM is given as 2. Ratio of those RPMs is 2. The ratio of torques on shafts is 0.5. Now we have to find the ratio of the power transmitted by the shafts. So they have given two data, the ratio of revolutions and ratio of torques applied on shafts. By using those two data, we have to find the power transmitted, or the ratio of the powers transmitted by the two shafts. Here the answer is option C1. Now let's see the formulas. Like power is given by P is equal to 2 pi nt by 60. So what is N? N is the uh, uh, revolutions in RPM. Then only we have to divide it by 60, so that we can get the revolutions in RPS. So here T is torque. Now we have the following ratios, like revolution ratio and torque ratio, and N and T are directly proportional to power. So that's why PA by PB equal to NA by NB into TA by TB. We have NA by NB as 2 and TA by TB as 0.25. Then 2 into 1 by 2 equal to 1. So therefore power ratio is 1. Now let's see some other points. 1 HP, that is 1 horsepower is equal to 746 watts. So this is a conversion factor that to be followed in case we want to find the power in horsepower, because if we substitute all the things here like rotations and the torque, we get the answer in watts. If you want to find that watts in HP, then we have to follow this conversion. 1 horsepower is equal to 746 watts. And this is also another formula. Actually this formula and this formula are same. P equal to Tm into 2 pi f. What is Tm? Mean torque into 2 pi into f. F is the frequency. Frequency is given by n by 60. Frequency unit is hertz. Suppose they may give revolutions in frequency, so then we have to find this formula so that we can get the answer for power. Power is equal to mean torque into 2 pi f. These are the basic points regarding power transmitted by shaft. Now let's move to next question. This question is based on shafts in parallel and series. Consider a stepped shaft to have twisting moment applied at B. So this is a stepped shaft. Here one AB one shaft and BC another shaft with different diameters, and at B they are applying torque of 10 Newton meter. And here they have given the material properties like shear modulus as G is equal to 77 gigapascal, and we have to find the angle of twist at C. Here what will be the angle of twist, that we have to find. This concept is this question is based on the concept of shafts in parallel, shafts in series. We have to use that concept to evaluate the answer for this. Here the angular twist at C is found as option D, 0.2368 degrees. Now we shall see the concept of shaft in series and parallel. Since the shafts are in series, here the shaft in series. What actually shafts in series means? When the shafts are in series, then the angular twist will be the sum of the individuals. For example, the angle of twist in AB plus angle of twist in BC is equal to angle of the whole twist, like AC. That is, here you can see the relation. Theta A is equal to theta AB plus theta BC. And total torque will be one and same. For example, here one torque. So that the same torque will be applied here also. So that is why total torque will be one and same. T is equal to T1, T1 equal to T2. In case the shafts in parallel, then angle of twist will be same, but total torque will be a summation of individual torques. Now let's get back to the question. Let's see the answer. Theta is equal to TL by Gj. How this relation is got from pure torsion equation. So here we have to apply torque as 10 Newton meter. So that is why 10 into 10 power 3 into 500 into 32. Because we have to find only the theta AB, because there is no torque applied in BC. That's why theta BC is 0. So let's find theta AB, TL by Gj. Length of AB is 500 mm. Gj equal to Gj is nothing but G is given as 77. J is pi d power 4 by 32. So here 32 is gone upward. So pi d power 4 divided by 32, that 32 is gone up numerator. So just substituting the values so that we can get the answer for angular twist. So J is equal to pi d power 4 by 32 in case of solid shaft. What is D here? Diameter of the solid shaft. So we are getting the answer in radians. So to convert into degrees, 180 by pi. We get the answer in degrees, 0.23698. And the theta BC is 0 because there is no torque applied here. Because T is equal to 0, then theta BC is 0. When shafts are in series, angle of twist will be theta AB plus theta BC. So here the answer will be 0.23698 degrees. So option D is correct. And this is a pictorial representation for shafts in parallel, because you can see here the torque is applied, and this is one shaft, and inside which there is another shaft is there, which is made of different material. And if the torque is applied, a T torque is applied, then the angle of shift will be same, angle of twist will be one and same for both this shaft. So that means both are in parallel. So this is the concept behind shaft in series and shaft in parallel. If they are in series, then angle of twist will be the summation of individual. If they are in parallel, then angle of twist will be the one and same for all the parallel shaft, but the total torque will be summation of individual. In case of series, here the total torque will be one and same. Now let's move on to next question. For the given loading diagram, the reaction torque developed at fixer in A is given as T naught L by A, and at B it is given as T naught L by B. Then what is the value of A plus B? We have to find. Here uniformly varying torque is given, as like we see in uniformly varying load. In case we have to find the bending moment. Similarly here they have given uniformly varying torque applied over the axis of the beam with fixed ends. Now let's find torque at section X. For example, say this has section X and X distance from A point. Then what will be the Tx? Tx is equal to Ta minus half into T naught by L into X into X. How this is? Because this is a triangular variation. Area of this triangle is half into B into H. So half into B is nothing but X. So half into B into this is H. T naught by L into X. That means what will be the torque over this section? That is nothing but T naught into X by L. And Tx is equal to Ta minus this area of this diagram at that section. Now we have to find the value of A plus B. And we know the end conditions. Both the ends are fixed. That means the angle of twist will be 0. A and B, angle of twist will be 0. So that's why theta AB is equal to 0. And what is angle of twist? TL by GJ. And we have T at X section. So that's why we are integrating from 0th position to Lth position. So that's why 0 to L. That is whole length of the beam. And Tx is given as Ta minus T naught X square by 2L into dx divided by GJ equal to 0. Then upon integrating, we get Ta into L minus Ta into L minus T naught by 2L. T naught by 2L is constant, and x square will be integrated as x cube by 3, and substitute the upper limit as L. Now we get the value of Ta as T naught L by 6. So that means A is equal to 6. Similarly, we can get the value of B equal to 3. How? Thus substitute this Ta value into here. Ta plus Tb is equal to T naught L by 2. How it is got? Again the area of the loading diagram. Half into T naught. This is T naught per unit length into this into base. Actually half into base. Base is L. Here half. This is base. This is height. So that's why T naught L by 2. Now we got the value of Ta and find Tb, so that we can get the answer for B as 3. A simple question, but a good concept. A plus B is found as 9. 6 plus 3. Now we shall move on to next question. If a circular shaft is subjected to an axial bending moment T and a bending moment axial torsional moment, sorry, this is torsion, and bending moment as M, such that bending moment is equal to 1.2 times torsion. Now we have to find what will be the ratio of maximum shearing moment to the maximum principal stress. This question is purely based on principal stress concept of accordingly to the torsional moment applied. A simple formula is there. You have to find that formula. so that we can find the answer for maximum shearing moment and maximum principal stress. Equivalent twisting moment. So before moving to these things, we shall see the base equation. Principal stress is given by this relation, sigma 1 comma 2, or we can say minor principal stress, major principal stress. Sigma 1 is major, sigma 2 is minor. So sigma 1 is equal to 16 by pi d cube into m plus root of m square plus t square. In case we have to find minor principal stress, then minus will be minor principal stress, then minus will be followed. So 16 by pi d cube into m plus root of m square plus t square. We know the value of m. We know the ratio between m and t, that is 1.2. So we can just substitute here, or we can even calculate this equivalent twisting moment. Equivalent twisting moment, in case of we have m and t, then what will be the answer? Root of m square plus t square. And in case of equivalent bending moment, what will be the formula? M is equal to half into m plus root of m square plus t square. These are the basic and important formulas we have to memorize so that we can easily find the answer for the question like this. And so the ratio, that is tau by sigma. Actually, tau by sigma is tau, we know, 16 by pi d cube into root of m square plus t square, and divided by this. So 16 by pi d cube and 16 by pi d cube get cancelled out. Therefore, root of m square plus t square by m plus root of m square plus t square, because we are considering only the maximum principal stress. That's why here plus. On substituting the ratio between m and t over here, we get the answer for 0.566. So these are some important points regarding principal stresses and equivalent twisting, equivalent bending moment formula. Now we shall move on to seventh question. A stepped steel shaft is subjected to a clockwise torque of 10 Newton meter at its free end. Shear modulus of steel is 80 GPa. Now we have to find the strain energy stored in a shaft. This question is purely based on strain energy. How much strain energy is stored in this stepped steel shaft? That we have to find. So we have to use strain energy formula here and substitute the known given data so that we can find the strain energy. Strain energy is given by U is equal to integration 0 to L T square x by 2 Gj dx. Or we can follow this formula in terms of tau. Here this formula is in terms of torque applied. This formula is in terms of shear. Now we have only the torque, so that's why we can use first formula. U is equal to integration 0 to L T square x by 2 Gj dx. And we have two shaft, like uh, they are stepped each other. So first shaft 0 to 100 mm, and next again 0 to 100 mm, that is L1 and L2. T square x by 2 gj dx, and find the integration value so that we get the simply like T square L by 2 gj. And for individually we have to denote L1 J1 like this, and just substitute the values. We have a T as 10 Newton meter. This stepped shaft is in series, so that's why torque is one and same all over the stepped shaft, so that's why T is same. Here also 10, here also 10 Newton meter. L1 is 100 mm, L2 is again 100 mm, and J all also same, because we are using the same material shaft of shear modulus 80 GPa. So we know all the things over here, just to substitute so that we can get the answer for strain energy, that is U value as 1.73 Newton mm. Now we shall see more other strain energy formulas. Strain energy per unit volume, that is nothing but shear resilience. The other name of strain energy per unit volume is shear resilience, that is equal to tau square by 2g. Tau square by 2g, that is what? Newton mm per meter cube. So that's the unit, tau square by 2g. and next is the this u is equal to half into theta, and this is analogous to in axial loading or transverse load. In transverse loading and bending moment strain energy, we follow like half into p del. That is analogous to here also, half into torque into theta. There we are considering the transverse load and deflection, that is half into p del. Here torque and angle of twist, half into t theta, just analogous to each other. And another formula is u is equal to tau square max by 4g into volume. So this is based on the maximum shear stress. Maximum shear stress occurs at the outermost fiber, and these formulas are based on solid shaft. In case we are getting a hollow shaft, then this factor has to be multiplied. R naught square plus Ri square by R naught square. R naught is the outer radius, Ri is the inner radius. So here you can see R naught square plus Ri square by R naught square is always greater than 1, right? Because R naught will be greater than Ri, then this ratio will be always greater than 1. That means the strain energy stored in a hollow shaft always be greater than a strain energy stored in a similar solid shaft. So that's why hollow shaft is more economical. We shall see more details on hollow shaft in the next upcoming question. Now let's move on to next one. One shaft is solid and other is hollow. Both have same weight and material. Hollow shaft has cross section with the internal to outer diameter ratio 2 by 3. The ratio of maximum torque carried by hollow shaft to the solid shaft will be. So this question is purely a comparison between solid and hollow. We have to find the ratio of maximum torque carried by hollow to solid shaft. In the previous question, we have discussed about the strain energy of hollow shaft. Hollow shaft will be more economical. Then obviously the ratio of maximum torque carried by hollow shaft to solid will be more than 1 only. So here option B is the correct one, 1.94. Now we shall see the calculation part. First, we shall calculate the area. Area of hollow shaft is what? Pi d square by 4 in terms of outer diameter minus inner diameter, because we are minus inner diameter, and we get pi 5 pi d naught square by 36. How? Because we have the ratio of inner diameter to outer diameter is 2 by 3. So just to substitute di by d naught is equal to 2 by 3 here, so that we can get the answer in terms of only d naught, that is outer diameter. And similarly we can calculate the JH, that is polar moment of inertia for hollow shaft, that is given by pi by 32 into d naught power 4 minus di power 4. So here also just substitute di by d naught equal to 2 by 3, so that we can get the answer in terms of what? Outer diameter. And this is in case of hollow shaft, and in case of solid shaft similarly AS and JS. So they have mentioned as same weight and same material. Same weight refers they have same area. So that's why AH equal to AIS. This is the concept, yeah, important concept behind this question. Same weight means they have same area. Same area refers to same volume actually. Per unit length, what will be the area? That's why we are calculating in terms of area. AH equal to AS. So we can get the answer in terms of outer diameter of the hollow shaft and diameter of solid shaft. So D naught equal to 1.3416 ds. Just you can pause this video and calculate all the things, so that you can get the answer like this. And in case of JH for JH is equal to pi d naught power 4 by 32 into 65 by 81 for hollow shaft. So just substitute d naught as 1.3416 ds here, so that we can get expression like this. And for same stress condition, tau is equal to tau h, and tau is equal to d by j, j. This is got from the pivot torsion equation. That is what is pivot torsion equation? T by J equal to tau by R is equal to G theta by L. So here just proportionate all the things like tau is proportional to diameter and inversely proportional to polar moment of inertia, and that's why tau max for hollow divided by tau max for solid shaft is equal to ds by dh into js by jh. That is just you have to consider this pure torsion formula. Here r is there, just in terms of diameter also you can get the answer. This is torque, this is polar moment of inertia, shear stress, and radius. So we can get the answer for T max, tau max for hollow by tau max for solid shaft as 1.94. From this ratio also we can interpret that hollow shaft has more shear stress than solid shaft. That's why hollow shaft is more economical. Now we shall move to next thing. This question is based on a thin tube. A tube of 3 mm thick is shown below. So this is a tube having 3 mm thickness, and the shearing resistance caused by a torque of 600 Newton meter will be. Here we have to find the shearing resistance of the thin walled tubes. Here different formula will be used. Let's learn about that also. Here the answer is option D, 52.24 megapascal. Now let's see what are the concepts and the formulas behind thin wall tubes. For thin wall tube, torque is given by 2 am into T minimum into tau max. So what is AM? AM is the area bounded by mean line. So here you can see this dotted lines are the mean line. So area bounded by mean line is denoted as A suffix m, and T minimum is the minimum thickness. Here 3 mm. This is the T minimum. And what is tau max? Shearing resistance. That has to be found here in this problem. And torque is given as what 600 Newton meter, and we have first we calculate am, that is 80 into 10 plus 10. How? This is 80 and this distance is that is the diameter of this circular, therefore 80 into 20 plus this circular. So here one semicircle and in right side one semicircle, so that's why pi into 20 square by 4, pi square by 4 is the area of circle. Therefore, we get the answer for AM. So just substitute here. T minimum is 3 mm and torque is 600 Newton meter, so that we can get the answer for tau max as 52.24 megapascal. A simple thing but important. Here the area bounded by mean line calculation is the most important. How? First we have to consider this rectangular area, and then the semicircle here and another one semicircle. So both together we get the circle. So that's why pi d square by 4. And these two are the other important formulas behind thin walled tubes. One is ZP, that is polar moment of inertia. Section modulus in case of this ZP is polar section modulus. So 2 pi r square t. This is the section modulus in terms of torsion. And the next is the U. U is strain energy. Strain energy in case of thin wall tubes is T square L by 8 am square G into summation of S by T, where S is the surface area. Here what is the surface area? One second. Surface area is given as 80 into 3. 80 into 3 is the surface area of this portion. So similarly, we have to calculate all the portion bounded by the mean line. So surface area is S and 80 by 3. For example, say this. This is okay. We have to calculate strain energy and section modulus in terms of torsion. So this is the main things regarding thin wall tubes. Now we shall move on to the last question. If a solid circular shaft and a hollow circular shaft have the same torsional strength, then what will be the correct one regarding solid versus hollow circular shaft? In the previous both the questions we have seen things regarding hollow shaft. So here also on hollow shaft question, here option B, C, D are correct. External diameter of hollow shaft is way greater than solid shaft because when they have same torsional strength, external diameter of hollow shaft, that is D naught, will be greater than ds. This we have seen in one of the previous question, like d naught is equal to some 1.42 into ds. So that's why d naught is greater than ds. And stiffness of both the shafts are equal, and the strain energy of hollow shaft will be always greater than solid shaft of same strength. That's why they are more economical. Here you can see the shear stress distribution. Here at the middle point, when radius is nearer to 0, tau will be 0. But here there will be no point in which tau will be 0. There will always be a minimum shear stress. So that means material is fully utilized. That's why hollow shaft is more economical compared to solid shaft. So in this video we have seen almost all the concepts, formulas, more important points regarding torsion. And please stay tuned for next videos and please subscribe the channel. Thank you for watching.